Our last section will deal with limits at infinity. So this time we're looking at the behavior of a function as the x's increase or decrease without bound. So the notation looks a little bit different. Now down here we have the expressions of infinity to tell us, like for instance, when x approaches negative infinity, what's happening as we move off to the left of the graph, or as x goes to positive infinity, what happens as we move off to the right of the graph. Now I've written L here, but not all these limits will work, okay? Some will exist, some won't, as always. But again, today we're looking at when x becomes big or small, what are the y values doing? So to illustrate that, let's look at a couple different examples. So here we have a pretty familiar graph we've seen before, but this time we're going to look at the behavior of f as x goes all the way to the left, as approaching negative infinity, and likewise moving all the way to the right as we approach positive infinity. Well, looking at the graph, as we go all the way off here to the left side, you can see it just gets closer and closer and closer and approaches 0. So the limit as x gets infinitely small means the y values are going to 0. Now going the other direction, as we go off to the right side of the graph, as x becomes infinitely large, again, we're slowly getting closer and closer and closer and approaching 0. So both the left and the right have the same behavior. That's not always the case, but you definitely want to know which side you're looking at so you can understand the right behavior. So here's a different example. Here we have a graph that's exponential, right? It's got a horizontal asymptote and definitely increasing this way. So when we talk about the behavior of g as x goes to negative infinity, we can see it's moving down here and leveling off at that horizontal asymptote. So we can say the y values are approaching 1. Now, if we go the other direction and we let x become positive infinity and move off to the right indefinitely, the y values just keep going up and up and up and up, and it increases without bound. So technically the limit does not exist, but like we talked about in our previous section, we can describe that as positive infinity increasing without bound. Now, to determine these sort of limits analytically, we want to know what to look for. So we'll begin with polynomials. So this right here is just a general polynomial of degree n. So without having a graph, if we want to determine what it does as the inputs, right, the x values become infinitely big or small, what we do is we focus in on the leading term. So if we want to talk about what is the behavior as x becomes infinitely small for this p of x, we just say what's the limit as x becomes infinitely small of this one term. And the reason for that is because for polynomials, way on the end, the end behaviors of their graphs, way as x gets really big or small, that's overall determined by that highest degree. So you want to look for that biggest power, and that's really what's going to be the driving force between those outside overall kind of how things end up. The interior part with the ups and downs, that's obviously determined by all these additional things on the inside of the polynomial, but you want to look for that leading term. And the same is definitely true for when you want to go toward positive infinity, right? So we just look at that leading term here for each one. So as we do this, you're just going to focus in on visually what's the limit of the leading term for each one, and that can tell you exactly what's going to happen in the polynomial. So a best way of kind of summing it up is to say that at infinity, the polynomial will absolutely behave as its leading term. Now, please make sure you realize that not all polynomials are always written in descending order of power, so make sure you correctly identify what the leading term is, the highest degree, and the highest power, that's the degree, and then that's what you want. Now, to help us understand what the answers are, we have to remember what the graphs will look like, okay? So I'm going to use graphs here to explain this, but this is something that kind of has to happen in your head so you can determine the behavior, because there's not a lot of, analytical work to it. You just got to recognize what you're looking at and understand how that, translates into what the graph is doing. So first off, let's look at an odd degree, okay? Which means that the end behaviors are going to be different. Now, when you have a positive leading coefficient, that means that from left to right, the graph, right, will start and kind of move up like that, which means that as we go toward the left, the graph's going toward negative infinity. So that means that this will always be negative infinity. As the x's decrease, the y's decrease. The other side, of course, moving to the right, we definitely are going up in an unbounded way. So when the x's are increasing without bound, so are the y's. Now, obviously, if we end up with a negative leading coefficient, the graph is flipped, right? That's just what happens with any graph when you have a negative in front. So we'll get the opposite. As we go to the left, we actually end up with going to positive infinity. So as x gets smaller, the y's actually get bigger, and the opposite then is true here as well, because again, the graph is simply flipped. So the easy way to remember it is with a nice positive leading coefficient, whatever the x's and y's do, they do the same thing. X gets smaller, y gets smaller. X gets bigger, y gets bigger. And if you put the negative in there, you flip that idea. Now with even polynomials, they do the same thing. So here we have a positive leading coefficient. As you guys can see, whether I'm going to the left or the right, the y values are increasing without bound. So with a positive leading coefficient on these, that means that whether x is getting bigger or smaller, y's are both increasing without bound on both sides. And of course, if you flip it over, you get the opposite. That means the even graph here, whether I'm going to the left or the right, both sides are decreasing without bound. Okay, so let's try some examples. So our first one, we're going to be looking at both the left and right end behaviors of this graph. But remember, all we care about is the leading term. So I'm really going to ignore the rest of the polynomial and just say, well, what's going on with 4x squared? Well, just as a reminder, 4x squared, that's just a graph that's a parabola, right? It's even. It's got a positive leading coefficient. So if it helps to maybe make a little sketch like this, go ahead and do it. But what I care about is that no matter if I go all the way to the left or all the way to the right, the y values are increasing without bound. So that means both of these are positive infinity. Now in our second example, we're just going to, again, focus in on negative 2x to the fifth. And as I did a moment ago, if it helps, make a little sketch to kind of help yourself visualize what's going on. It's not a bad idea. Remember, this right here is an odd graph, but it's also got a negative leading coefficient. So that means it's going to start up here and kind of go down. I know that's not exactly what it looks like, but it gives me at least an idea on the ends, right, the beginning and end of the graph, where it starts and ends. So on this graph, because it's a negative and an odd, we start up here, we end down here. So as I move my x's all the way to the left, right, negative infinity, it's going to go to positive infinity there. So that means this is going to be a positive infinity. And as I look at the graph and go all the way to the right with positive infinity, the y values are decreasing without bound. So in this case, this one would be negative infinity. Because again, when you have that negative coefficient, they kind of do the opposite. As x gets bigger, y gets smaller, and as x gets smaller, y gets bigger. Now for our third example, we have a positive leading coefficient with an odd degree. Okay, so again, if it helps, when I visualize the graph and see kind of what's going on, that means I have an odd function, but it's positive, so it kind of works like that. Which means that, again, as I'm focusing in just on this, as x goes to the right, the y values increase without bound. As x goes to the left, the y values decrease without bound. So in this case, because it's a positive odd, they do the same thing. Now in our last example, we're going to just focus on this negative x to the fourth. So in this case, it's going to be a negative even graph. So that means whatever it looks like, it's going to be going like that. Where whether I go all the way to the left or the right, because it's even, they're going to do the same thing. Because the leading coefficient is negative, the y values will be decreasing without bound both directions. So that means on this one, both of these are going to end up being negative infinity. Now, the more common style limit you're going to run into with this sort of thing are rational ones. So the most common situation in calculus when we talk about end behavior and limits at infinity do come from rational situations. So these usually happen when the limits, of course, are going to be infinity over infinity because we're letting x become infinitely big or small. But in order for us to figure out what's going on, we sort of do the same thing. We're going to focus just on the leading terms, but we're going to be looking at the leading terms of both the numerator and the denominator. Now, depending on how the degrees of the numerator and the denominator interact with one another, there's three different outcomes that could happen. Now, the first one is that the degree of the top, right, is smaller than that of the bottom. So the degree of the denominator is bigger than the degree of the numerator. When this happens, the limit will always go to 0, okay? Anytime your bottom has more power to it, you're going to end up dividing by more and more larger numbers compared to the top, which, again, just makes you divide by larger and larger values, taking you to 0. So an example of that will look something like this. Okay, so again, technically what's going to happen is we're going to do the limit and x is going to be becoming infinitely big, but we're just going to focus on the leading term on the top, 8x, and the leading term on the bottom, x to the fourth. Okay, those are the terms that have the biggest power. Now, when you think about this, this actually simplifies to be the limit as x becomes infinitely big, and we can cancel out next there, and this is just 8 over x to the third. So just like we talked about in our previous section, when the bottom becomes infinitely big, we know that this thing is going to be going to 0. Now, the next thing that could happen would be when the degrees of the top and the bottom have the same, right? They're the same number. So whatever the degree on the top is and the bottom, they end up being the same value. So even if you did want to simplify, this is when you actually end up getting a number. So for example, right here, if we did this and we just focus in on those leading terms at the top and bottom, we end up with really an 8x as a leading term on top and an x on the bottom. Well, again, we can simplify and cancel out one of those x's, and this just becomes a horizontal line. So that means this works out to be 8. Now, the big picture, though, that I want to take away from it is when you look at this right here in the unsimplified version, it works out to be the ratio of the coefficients. So really, your eyes should be looking right here and just saying, well, okay, the powers are the same. What are those leading coefficients? And that's where the limit's going to go. And this doesn't matter whether you're going left or right. It's going to wind up going to 8. Now, the last scenario is when the degree of the bottom is actually smaller than the degree of the top. Now, when this happens, there is no limit. It is going to be d and e. Now, we still want to, as always, try and describe it. So what you want to do here is simplify it. And when you do that, it should end up looking like a polynomial. And we can do what we just did on our previous examples and look at the leading term, think about what the shape of the graph is, and either answer positive or negative infinity. So for example, let's say we had 8x squared over x. Okay, so again, we're going to focus in on this right here. Clearly, the top has a bigger power. So as we're thinking about the limit as x goes to infinity, if you simplify that, we just get 8x because the x's here can cancel. Well, 8x, right, that's going to be a positive odd graph, so it looks like this. And since I'm going towards x being positive infinity, I can say that this is increasing without bound. So essentially on that scenario, simplify and treat it like a regular polynomial. Okay, so let's try some examples. Now, the one thing I really want you to notice, especially with these, now that we've already talked about a couple ones before, is that as we do this, you don't really need to do much work at all. All you have to focus in on right here is the leading term. That's all you have to look at. So in our first example A, we can see that, okay, the bottom has a bigger power than the top, so we don't need to worry about doing any other work other than say it goes to 0. In our second example, the leading term on top is the negative 3x to the fourth, and the bottom, the leading term is x to the fourth. This is an example you got to be really careful not to assume it's always a front number, it's the biggest power. But again, looking at negative 3x to the fourth and x to the fourth, they are the same power. So when you look at that and notice, hey, they have the exact same degree, the end behavior is going to be the ratio of those leading coefficients. So it's going to be a negative 3 on top and a positive 1 on bottom. Or if you'd like to simplify it, you can simply write it as negative 3. Now, for our last example, I want to talk about one that's kind of different. And the reason for that is that this one actually has different end behaviors depending on which way you go. Now, with all of these, it doesn't matter if we had gone to positive or negative infinity, all these things would remain the same. The only time you might get different end behaviors, whether you go to the right or left, is when you have this sort of radical situation with a squared with a square root or a fourth power with a fourth root. Because when you simplify these, you're going to have an absolute value. And when you have the absolute value, the top and the bottom don't necessarily do the same things. Okay, so first off, as always, my eyes are definitely still going to go here. Okay, we're going to focus in on those leading terms. But it's important when I rewrite this to make sure I'm careful how that how it simplifies to be, because I've got to understand in the denominator, this is a square root, and square roots cannot produce negative numbers. They can only produce positive numbers. So I've got to take that into account when I kind of rewrite this. Okay, so in the top, I have a 3x. Now in the bottom, I have just a square root of 2x squared. Now that means I definitely have the square root of 2. However, if you take the square root of x squared, you might think, oh, that's just x, and they have the same power. And that is the kind of thinking you want to do. However, in addition to recognizing technically it works out that they have the same power, this needs an absolute value on it, because we can't just say it's x, because if I said it was just x, it could be any number. But we know that this value in the denominator is coming from a square root, and they only produce positive numbers, right? There's no negatives that can happen there. So you have to put the absolute value just to remind you, yes, it simplifies to simply be an x and have the same degree as the top, but it's absolute value. And of course, that's going to be this exact same thing here, whether we're looking the other direction. And that's a really important step to make sure that you analyze it correctly. Okay, now that being said, let's look at what happens. So in this one, it is going to go to the leading coefficients because, as always, they have the same power. So the answer here is going to be a 3 over a negative 2. Likewise, this one's going to be a 3 over a negative 2. But what makes them different is this. In the top, x is becoming more and more positive, right? It's increasing without bound. Now, when x becomes more and more positive, the top remains a positive number as it gets bigger, and so does the bottom. So it will just be 3 over radical 2. However, in the bottom, x is approaching negative infinity, which means it's going to have negative values. Now that makes the top negative, and that's fine, but it doesn't make the bottom negative. They're not going to do the same thing because the absolute value is going to remove that negative. So in this case, what happens is the top, the x's are changing or becoming negatives, the bottom become positive, so the number stays the same, but it's going to be the opposite because the signs are not the same. Here, they're both positive. Here, one's positive, one's negative. So it is going to still take that leading coefficient idea, but you have to put the negative on there. Now, a couple things. Let's look at some trigonometric situations that don't really apply to being polynomials or rationals. First off, oscillation is no limit. Okay, I know we talked about that before as being one that does not exist, but there is no description for this. So cosines and sines, graphs that simply oscillate, there is no way we can describe that in any way other than to say it does not exist. Now, there are some scenarios that we can get some answers, but we have to use the squeeze theorem. Because again, looking at this, the top, right, the sine x is oscillating, so that doesn't really give us anything. The bottom is definitely, doing this infinity idea, but that's an indeterminate thing. We don't really know the answer. It's not behaving right. So what we want to do is use that squeeze theorem. So the way you want to think about it is this, right? So we know that we have the sine of x, and we have to come up with a relationship. Well, I'll tell you right now, the first thing that jumps out at me with the graph of the sine of x is that it has a bottom and a top of 1 and negative 1 like cosine. So I know it's always going to be greater than or equal to negative 1 and always be less than or equal to positive 1. Now, obviously, I'm looking for sine x divided by x. That's the actual thing I want to know the behavior of. So if I take my sine x and divide it by x, now I'm talking about what I want. But to maintain the compound inequality, if I divide the middle by x, I got to divide the outsides by x to make sure it's the same. Now, here's where I can get my answer. Now, remember, with squeeze theorem, if I don't know what's going on here in the middle, what I hope to know are the behaviors of the outside. And if the behaviors of these outside expressions go the same place, right, they squeeze this in. Well, remember, these are rationals, and the power is definitely bigger in the bottom, so both of them go to 0. So this one, as x becomes infinitely big, is approaching 0. This one here is doing the same thing. And since sine of x over x is always bounded on either side by them, if both of them are approaching 0, so is this. So in this case, my answer here is it goes to 0. So now that we've talked about limits at infinity, we can use them in a more definitive way to identify horizontal asymptotes. Now, this is something you've actually seen before in pre-calculus, and we simply gave you rules when you're looking at them to identify where these happen, but now you're actually seeing why these rules make sense in the context of limits. So what we're looking at identifying is a horizontal asymptote, so it'll be y equals a number, and the horizontal asymptotes really are the end behaviors of the graphs. So if you want to know where does the graph level off at either way, you're asking yourself what the end behavior is, what the limit at infinity or negative infinity gives, okay? So by doing the work we've just done, we're actually finding horizontal asymptotes. Now, as we've seen before, however, you can sometimes on either side go different places. So at most, you can have 2 horizontal asymptotes. Many functions only have 1, because we saw a lot of examples, it didn't matter which way you went. However, many graphs, of course, don't have any. So the options are there's no horizontal asymptote at all, there is 1, or with those radical ones like we saw, you could have 2. So let's try this example. Now again, this is just a function and they're asking where the horizontal asymptotes are, but really what we're going to do is we're going to say, all right, what's the limit as x becomes infinitely big of f of x? That's all we care about. And as always, this is just a visual thing. We look at the leading terms. Well, they have the same power, which means that this is going to end up being the coefficients of those leading coefficients, which means the limit goes to 5/3. So that tells me that what the line, right, y equals 5/3, that is the horizontal asymptote. Now, for our last example, we're going to look at something that I think you can see we saw earlier with that radical. We got to be really careful which way we go. So just like we did before, let's evaluate the limit as x goes to infinity. But we're also going to have to recognize that, the negative might be a little bit different. So we want to check that out. Now, looking at the leading terms, that's all we care about. So on top, we have an x. On bottom, we have the square root of 5. And as always, the square root of x squared is actually the absolute value of x. And we know that because it cannot produce negatives. So we got to make sure we're careful. So that means on the top one, it's definitely going to go to leading coefficient. The answer is going to be 1 over radical 5. But because x is becoming larger and larger and positive, both of these will be positive, okay? So that means that this one is going to be the positive 1 over radical 5. Now on the bottom, it's going to be the opposite because again, x is becoming smaller and smaller. So, the top is becoming the negative values, but the bottom remains positive. So when we put this together to get our answer, we can say that y equals either plus or minus 1 over radical 5 will represent the two different horizontal asymptotes for that graph.